And we are recording. Welcome to the first in the series of electronics mini lectures. I'm new to this. This is my first time doing this. I practiced a little bit, but this is going to be a little weird. So let's get started with reviewing what we were talking about the other day with diodes. So we have a diode. A diode is made of two types of semiconductor that have been fused together. We have a P-type semiconductor over here and an N-type semiconductor over here. The N-type semiconductor has been doped so that it has an excess number of electrons. The P-type semiconductor has been doped so it has an excess number of holes, that is to say electron deficits where you can put electrons in. So if we put a bias voltage across this diode, it will conduct current in one direction but not the other. So for instance, if I put a bias on it like this, right, so this is negative and this is positive. This way is the, which way, forward or negative? This is the forward biased because this thing injects electrons this way. So electrons are going this way. So electrons are being injected in, and so the electrons are going this way. Meanwhile, it's pulling electrons out over here. So the holes are going this way, and so holes are moving this way, and they can interact, and they can annihilate. They don't actually have to annihilate, which is one of the interesting things, is as long as the charge carriers can make it to this boundary, the positive ions, the holes rather, can go right through that boundary, and the negative ones can also go right through the other boundary. Because remember, this is still the same, basically the same type of silicon, with just a few extra bits added. So they don't actually have to annihilate. If they annihilate, that's when you get an LED. But you could just have the charge carriers just sweep past each other. And that's going to be important when we get to talking about transistors in a minute. Now, if we have the same situation and we put it under a reverse bias, that's the positive over here and the negative over here. Right, remember how the battery goes. So this thing now is attempting to pull electrons this way, and so electrons will get pulled over to the right-hand side of the N-type. Oh, let's use colors. Colors are fun. So N-type over here, and this thing is attempting to push electrons in this way. So holes are getting pulled to the left. So in the middle of this, you have what we call the depletion zone. Okay, my handwriting is still just as bad as ever. We have the depletion region in between here where there are no charge carriers and so no current can be conducted. If there's no bias, that depletion region is smaller, but it's still there. So this allows, in this situation, the diode can allow current to run this way to the right, but not to the left. And so this diode we would draw symbolically as that. Or in the above circuit, for instance, in the forward biased circuit, it would look like that. It would be that circuit. Now, of course, you should never build this circuit because the diode always has that small 0.4 or 0.6 volt voltage drop across it. And if this is a 5 volt supply, then in fact what we're doing is we're saying that these two wires are 0.4 volts apart and this is 5 volts apart, which means that something's breaking down. Which means that we have to consider the small resistance in these wires, or the small resistance inside the diode, or the small resistance inside the power supply. And of course those are small, so this thing so there's big voltage drops across them, so they'll heat up quite a lot. It'll conduct a lot of current and it'll heat up and go boom. So generally speaking, for instance, if we're running an LED, we would have connect to plus 5 volts and then have a resistor, say a 500 ohm resistor, that then goes, and so that's the circuit we have in lab 4. Oh, and if this is an LED, I'll draw those little symbols to show that it's shining. All right, so that's an LED. So that's a diode, right? That's a modern diode. Now, diodes have been around for a long time. Even before we had semiconductor, we had a way of doing this because we all had old tube radios. So in those days, we would have called it a valve. And how we did that was actually pretty straightforward. Okay, my picture here is in my way, so let's turn this around. So in those days, what you would have done is you would have had a tube. So you make a vacuum tube like this, and through the base of the vacuum tube, right? So this is a glass tube with the air evacuated. The glass is nice because it's easy to make, it's cheap, it's airtight, and you can see into it, so you can see if anything is busted. And then all you need to do is you need to put like a flat metal piece here, and you connect that to an output, and you put a flat metal piece here. and you connect that to an output, right? And then the only difference between these two pieces is under the bottom one, say, you put a heating coil. So I'll just put a current source in there to create the heating coil. So this lead and this lead are otherwise the same. Now this metal, because it's in contact with this heating coil, it heats up. And so so in this, the temperature is higher, and so you can have a higher chance of having an electron exit the metal because it requires enough kinetic energy. Now once an electron has exited the metal, it can travel freely to this plate. So electrons can travel from here to here, but the odds of an electron going this way are very small because this plate is cold. And you raise this thing up to a few hundred degrees, right? This is like in a light bulb. Light bulbs can get to, I don't know, 6,000 Kelvin or something like that. So this can actually be quite hot, and this can be quite cold. And of course, the heat doesn't transfer between these two guys very much because they're in a vacuum, so that all works. So that means electrons can leave this plate and hit this plate. So this thing, in fact, works like a diode, where it would be something like this, right? It would work like this. So this thing is the anode, and this thing's the cathode, or vice versa. I can't remember which one's the anode and the cathode on a diode. I'd have to go look that up again. So, so this was all accomplishable with 1910s technology. There's nothing preventing you from creating a diode this way. So what I'd like to do today is briefly get into the next steps for what we want to do for understanding electronic circuits. Now, up till now, we've discussed filters, so we know how to reduce the amplitude of a signal. We know that if we have an RC circuit, I can take a signal that's got some sine wave, and I can change it into a smaller sine wave, and I can take out the frequency components I don't like. But that always results in attenuating the signal, making the signal smaller instead of bigger. So now we would like to consider options we can have for increasing signal instead of decreasing it. Now the first type is a very easy one to understand, and so in Lab 4 I'm giving you an exercise to run through this. And we actually still use these all the time. It's called a relay. So a relay is actually a really simple device. We have two leads here. This is going to be our input. And we're going to take them and we're going to wind them around an iron core. So that makes us an electromagnet. And then we're going to have a switch up here. So let's say I've got two connections for the switch that can come out, and the switch is normally in this position. Okay, so we're going to have, so this is the control, and this is and these wires are going to be our output wires. Okay, let's make that bigger. So this, when you turn this circuit on, then it turns on this electromagnet, which will pull this metallic switch down. And when that happens, it makes contact with this other terminal instead of the first terminal is in contact. So this connection here, whatever it was, is broken, and this connection, whatever it is put into place. And this works. The problem with relays, so relays are still really good. So the reason they're really good is all you need here is just enough current to make this thing an electromagnet and pull this switch down. And in fact, you don't just have to have one connection. You could have two or three different connections in here all move with the same lever. So you could turn on and off many things. But there's the nice thing here is that there's no limit to how big these wires can be. Well, there's a little bit of limit. You can't have like a giant switch being pulled up and down. But these things can carry massive currents. So just huge quantities of current, whereas this thing can be quite small. So in fact, you might use this, and the place you might use it is if you have like an Arduino or a hobby circuit. So you have a computer that you want to connect to this part of it that will turn the relay on and off. And so this could just be like a plus 5 volt control signal that's coming from a computer. Whereas this can be wall current. This could turn on an electric light or a mixer. And so this could be like 120 volts over here. And so what you would do is you would connect these two things here. That switch, right, would just become part of your, so here's my light bulb or whatever, right, and then these go to the 120 volt wall supply. So relays are actually really good. So they allow you to transmit signals, and you can also play some funny logic. If this one turns on, then this connection turns off, and this connection turns on, right? So you can play the game either way, so that turning the signal on turns the output off, or turns the output on, or does both things, or does a whole bunch of things. So this allows you to control one device with another device and allows you to have a very high voltage and high current circuit being controlled by a relatively low voltage and low circuit current, low current circuit. The problem, of course, is that this thing takes a physical time to move up and down. Is that this, and also an electromagnet is actually isn't like a really light device. It's kind of hefty. So even this is not ideal. This would never, well, very early computers used things like relays, and they were incredibly slow because you can only switch this thing up and down a few hundred times a second, which isn't very much. So 100 hertz instead of the gigahertz that we have our computers running at. So this is, but these are still used all the time in your car. If you have, for instance, your power windows, the switch that controls the power windows controls the electromagnet here, and then the actual power window is a pretty hefty motor which runs through a relay. And so, in fact, you can hear this clicking sometimes in your car. If you have, if your power windows aren't working, you might hit the button and you hear a click, but the power window doesn't move, and that means you need to replace a relay. In fact, there's a box of relays and fuses that sit usually inside the cabin, sometimes up under the dashboard, or sometimes you get it through the glove box. And they often have spare relays in there. So if you get into this, you can figure out how to fix your own car when this sort of thing goes wrong. So these relays are really easy to replace. And in fact, the one I've given you in your kit is an automotive relay. So that's how a relay works. Now, there is also, right, so when we go to, again, 1910s technology, we can explain more easily than anything else what we would have used then. And so there, if we want a control circuit, and so there's two things we need. One is the relay allows us to turn things on and off, but we'd also like to have something where if we make a small control, we have a big output. So a small control leads to a very large swing in output. So we'd like to have it as an amplifier, not just as a switch. So in order to accomplish that, and also to accomplish faster times, what you would have done in sort of 1910s to 1950s technology is you would have had a vacuum tube. So a vacuum tube would look just like what we described before. So you have a tube like this, and I'm going to turn off my notifications here. Slack is clicking at me. So I have a tube like this, and again as before, I'll have one contact down here, and I'll have it under a heating coil. I won't show the heating coil wires just for convenience. And you have another plate up here. So far this thing just works like a diode, right? Oops, don't mean that to be connected. So you have a plate up here, and you have a plate down here. I forget which one's which. This is the this is the anode, and this is the cathode. And then so far this is just a diode, but now we're going to add one more element, and that's called the grid. And that looks like a grid. It's a wire grid that you attach in between, and you also attach, and you have it go down here as well. Now what you have is you can put a small negative voltage on that grid. And if you have a small negative voltage on that grid, then the electrons can't make it to the anode, or only a few of them can make it to the anode, depending on whether they hit a wire or they go through one of the holes. So what you're creating here is you're creating an electric field here which slows down and deflects the electrons and keeps them from reaching the anode. So if you put a small voltage on this grid, you can stop the current going from the electrode to the anode. And if you change that voltage, you can dial that voltage around so that you can let lots of electrons through or a few electrons through. So this is a vacuum tube, and this is what you would have used in transistor radios or early televisions. And it works. The problem with tubes, and in fact tubes are still used in a few specialized ways today. One of the advantages of a tube is there's almost no limit to how much current you can drive through this thing, because these are just electrons flying off a plate. So these wires can be really thick and heavy and massive, and you can drive a lot of current through here, still with small control voltages. So that allows you to, for instance, this is used in power amplifiers. So the klystron tubes that we use to accelerate particles at Fermilab, they use vacuum tubes as their primary power transformer. Their primary power amplifier comes from these things. If you go to a radio station, radio transmitters will often have transistor tubes as being the core transmitter for exactly this reason, because you have to push a lot of current up and down that massive antenna. There's a few other places this shows up. hobbyists, audio enthusiasts, for a while there was a real trend to using tubes in your audio amplifier equipment. The reasons for this are a little less clear. It does change the performance characteristics of the amplifier, and some people thought that led to a nicer sound. I think basically they just thought it was kind of cool and retro looking, and you can find some really pretty pictures of this stuff on the internet. Okay, so that's how an old style tube works. So let's move to a modern style transistor. So in a modern style transistor, we're going to use doped semiconductor again. Oops, let's get my papers here in order. So in this case, what I'm going to do is I'm going to again have P-type and N-type silicon, P-type and N-type semiconductor. Except now I'm not going to do it quite. I'm now going to have three sets. So what I'm going to do is I'm going to have an N-type over here, and I'm going to have a P-type in the middle, and I'm going to have an N-type on the right. And now I'm going to have three contacts. I'm going to label this one E, I'm going to label this one C, and I'm going to label this one B here. Okay, so now how are we going to do here? So what I'm going to do is these two here, this input and this input are going to be, these two are going to drive my input, and these two are going to be my output. So this is how I'm going to set this guy up. So what I'm going to do here is I'm going to put a small voltage here between these two guys. So this is in forward biased mode, so electrons are being ejected into this way and going, so I have electrons going this way. And here I'm creating holes in this P-type because I'm pulling electrons out of that. Now, on the other side, I'm going to put this guy. So this can be a giant voltage supply, a very high voltage. Now, normally, this thing, there's a depletion region right here, right? And so normally, I can't get any current through this junction. And so you see I've got this big voltage across here, and so I would normally be able to pull a very large current going around this way, which means that the electrons would be going clockwise through this thing, if I didn't have this depletion region, which is keeping me from moving any current anywhere. But here's how this works essentially, is these electrons that I've injected in here, they can keep going right through the P-type silicon and make their way over into the N-type silicon. So I now have charge carriers that can do this, and they can only get through this if I've got a voltage here to pull these, to create more charge carriers in this region. Basically, by creating a small voltage between here and here, we can create a big current between here and here. Now, the principle of this is basically the same as a vacuum tube. And if you're not following this completely, that's because I'm bad at explaining it, because I've never really had a firm understanding of this in the first place, to be completely honest. The important thing here is, though, that you have a small current, a small voltage here drives a large current here. Now, these three things, this is called the emitter, because it emits the electrons. This is called the collector, because it collects the electrons, and this is called the base. So the base is sort of your control line, and the emitter is sort of your source of electrons, which would, your low voltage side, and the collector is the high voltage side where the electrons come out. Now we have a way of showing this, right? So the diagram for this guy looks like this. We have a line with an arrow on it, and that shows the emitter. There's a horizontal bar. Coming out of the bar is the base, and this line is the collector, right? Or if we flip the whole thing left to right, we'd mirror image this. So this would be the emitter, and this would be the collector, and this would be the base. And this whole type of transistor is called an NPN transistor because it's got N, a P, and an N. You can also drive a very similar circuit with a P and P resistor, and that's got sort of reverse polarity. So you could use them in different applications. Neither one is superior to the other. They're just useful in different orientations. But most circuits actually tend to use only either one or the other just for convenience because it's easier to source one type of transistor than two. So to put this in context, how you have this in a circuit is you would have, so there's my emitter, and there's my collector, and there's my base. And what I would have is I would have some small supply voltage here. So this guy is forward biased like that. And then I have some resistor here so it can carry a current. And here's my big supply connected to there. And then this is my V out, right? So the more current that's being carried through here, the different how this voltage can change. So changing this small control voltage over here can massively change this large V out over here. So now we finally have the ingredients for an amplifier. Now you'll notice that one thing works here is that if this will only work in one direction, right? If I reverse bias this, then it won't run at all. So this amplifier would only work with positive going signals over here. So the solution to this is you run two transistors, and so you run something called like a push-pull amplifier, which requires at least two transistors. Now, in fact, these circuits are very complicated, and developing a transistor circuit that can do everything you need is really beyond the scope of this course. And frankly, I have never had instruction in it. But you don't need it, and the reason we're going to discover when we move to Lab 5 and we do operational amplifiers, which are kind of pre-built circuits with their own characteristics that are much more easy to understand than transistor circuits. That said, it's worth going through at least one application. And we have one of those. Oh, I don't have it in my notes. So we have one of those in the lab. So the last part of the lab actually has a transistor that's operating as a switch. And here the whole job is to give a little more oomph to a circuit so that with a small control voltage you can change a large one. And in fact, we're going to use that to drive the electromagnet in a relay. So that's part of the last part of Lab 4. And there is a small transistor in your kit. The transistor in your kit is a small unit that looks like this. So it's got 3 pins coming out the bottom, and the flat side tells you which pin is which, so you can orient it the correct way around. And there's instructions in the lab packet for how that works. A different kind of transistor that I actually find easier to understand, and one that's well worth discussing, is called a FET, which stands for Field Effect Transistor. So field effect transistor, this one's actually, I find this much easier to understand in terms of how this works. And the nomenclature for this guy is a little bit different. And in fact, he only needs a couple different types of silicon. So what he has is he have something like, so let's make, here's my transistor, and I have some region here which is going to be N-type, and the rest of it's going to be P-type. And so this means that I'm going to create a depletion region around here. So this is my depletion zone. So normally, so this thing acts as a diode, except now I'm going to put my connections in different places. Now I'm going to put a connection up here, and I'm going to call this the drain, and I'm going to put a connection down here, and I'll call this the source, and I put a connection right here, and I'm going to call this the gate. So how this works is, under normal conditions, right, this thing acts like a conductor. It's got charge carriers due to the P-type semiconductor. There's holes in here, and so I can have a current flowing through here. But if I put a voltage onto this, what this distortion, this bit of stuff, now it won't, if I put a voltage on here that's, say, a positive voltage, right? What it'll do is that'll suck the excess charge carriers out of here and widen the depletion region. But by doing that, I've got this positively charged field. So what happens is that field starts extending through the rest of this, and so I've got this, again, this high voltage field. So this is exactly like the grid when we were talking about vacuum tubes. So this leaves only a small passage for the current to go through here, and so it squeezes it. So this is like taking a garden hose and squeezing it with the water running through. As you squeeze the available area, it reduces the current. Essentially, it increases the resistance of this thing. So now you have something you can control for this. Now, the reason field effect transistors are important These were later developments. The original NPN, PNP transistors is what you would have found in a transistor radio in the 60s and 70s. The field effect transistor turns out to be much, much more important going forward into the 21st century, or the late 20th century, early 21st century. In particular, there's one type of technology called a MOSFET, and this stands for metal oxide semiconductor. So metal oxide semiconductor field effect transistor, or a MOSFET. And the MOSFET technology is really nice, in particular because it's very easy to manufacture. So what you can do is you have this whole thing. So if you just need a substrate of P-type silicon and you need to implant some N-type silicon, or you can have a bilayer of N-type and P-type silicon, and you can etch off with, say, electrons or a laser or laser light or something like that. You can etch off this part, cut it away, and then just leave your field effect transistor. And that's how you make computer chips. These computer chips are made out of sets of substrate where they have cooked off different parts of the transistor. Field effect transistors are really nice because they're very sensitive. So these are not good power components. These are not very good for getting large quantities of power, but they are excellent at very small signals, and they have very fast switching time.